Hi, everyone. I hope things are going well for you. We've been talking most recently about magnetostatics, and today I'd like to actually finish up our discussion of this subject. Wow, okay? And after this, we're going to move on to talk about time-varying fields. That'll be really interesting, of course. But for today, what I'd like to do is to continue our discussion about vector potential, and then finish up by talking about magnetic boundary conditions, how the magnetic field changes when we go across the surface from one material, say, into another. In any event, that's what I'd like to do. Here, let's take a look at an outline. All right, so in magnetostatics, we first talked about magnetic forces. For example, the force on a point charge, F equals Q V cross B. Okay? And more recently, we've talked about magnetic fields and introduced the Biot-Savart law, which lets us calculate the magnetic field produced by currents. As in this formula here, okay? And following that, we developed Ampere's law, which tells me that the integral of the magnetic field around a closed loop is equal to mu naught times the current enclosed by the loop, okay? And from the Biot-Savart law and from Ampere's law, or really another version of Ampere's law, we found the following. We found some properties of the magnetic field, that its divergence is always zero, and that the curl of the magnetic field in magnetostatics is equal to mu naught times the current density, J. Okay? Most recently, we've talked about the vector potential. The vector potential, we said, was defined through this relationship. The curl of A is equal to B. So A is a vector function whose curl is equal to the magnetic field. That's how it's defined. Okay? And we learned how to find the vector potential from the current. We'll talk about that again in just a second. Okay? Now today, what I'd like to do is to show you that many of the tricks that we used before to find the electric potential can be used to find the magnetic vector potential. And in particular, we can write a multipole expansion of the vector potential, which lets us find the vector potential when we're far from some distribution of currents. Okay? And we'll use this to define something called the magnetic dipole moment. And then we'll find the magnetic field produced by a magnetic dipole. Okay? The last thing we'll do as we finish up is I want to briefly talk about the boundary conditions on the magnetic field. All right. So, well, that's what we'll do. Here, let me stop this short video and then we'll continue in the next.